So last time we looked at how to get electrons to move in a wire, and that's an interesting problem, but it's really fun when you take these wires and you use them to create a circuit. So here I've created a circuit with 3 branches. The way we're going to envision the circuit is that we have a battery located over here in the left branch, and then we have resistors over here in the middle branch and in the right branch. And the electrons are able to switch between the different wires when they get to the corners. So basically when an electron comes from this wire up to this wire, it's able to switch from one box to the other in this little intersection. When an electron ends up in this intersection, it's got a random chance of ending up in the red branch or in the blue branch. And so the question is, if we set up this circuit this way, can we get the same result you would get if you had solved this circuit as a problem? And it turns out you can. We'll show that at the end of the video. But what you need to do is figure out what the voltage is in each of these wires. Meaning I need to figure out what the voltage is across this wire, voltage across this wire, voltage across this wire, across this wire, across this wire. You guys remember, when we create these wires, we have to specify what the wire's voltage is, how much voltage it's experiencing. And that's going to be different for each of these because they've got different resistances, right? So as you discovered last time that if you make this wire twice as long as this wire, it's going to have twice the resistance. So before we can look at the results of this, we're going to have to solve this circuit problem for ourselves. So first, let's place the battery for our circuit in the left branch. Each wire in the circuit has a resistance of either R or half of R based on its length. The current will flow out of the battery and split at the top junction. Conservation of charge means that the current in the left branch is equal to the total of the current in the middle branch and in the right branch. Let's call this equation 1 for future reference. Next, we can look at the voltage gains and losses around each loop of the circuit. The left loop will gain voltage from the battery and then lose voltage across each of the resistors. Conservation of energy says that these voltage gains and losses must add to 0. Let's clean up this equation a little and call it equation 2. Now we look at the right loop. The right loop loses voltage when going around the right branch, since the loop goes in the same direction as the current. On the other hand, this loop gains voltage when crossing the middle branch, since the loop goes opposite the current here. Let's call this equation 3. We now have 3 equations and 3 currents, so we're ready for some algebra. Equation 3 is the simplest of all the equations, so we'll start with it. With just a little algebra, we can now rewrite I1 and I3 in terms of I2. These substitutions will allow us to transform equation 2 into something we can solve. Notice that the only current left is I2, so we can solve for I2 in terms of the battery voltage and the resistance R. Once we have I2, we can easily get values for I3 and I1. Again, notice that all of our final answers are in terms of the battery voltage and the resistance R. The last step is to use Ohm's law to calculate the voltage across each resistor using the current in the branch times its resistance. Notice that all the R's cancel and every voltage is given in terms of the battery voltage alone. These voltages are the last bits of information we need for our simulation of this circuit. And so that's what we've set up here in our gray branch over here on the left that contains the battery. We've got a voltage of 3/16 times the battery, 3/16 times the battery, and then 3/8 times the voltage of the battery for the longer one, because a longer wire needs to get more voltage. Then we make the middle branch, and that's going to have 1/4 of the battery's voltage. And then we make the right branch in blue, that'll have 1/16, 1/16, and 1/8 of the battery voltage, again with the longer wire taking up more resistance and therefore taking up more voltage. And so when the current graphs eventually appear, we see that our predictions from the solution are borne out. The current in the right branch here in blue is about 1/3 of the current in the gray branch up here in gray. Meanwhile, the current through the middle branch here in red is about 2/3 that of the current in the gray branch. And if we take kind of this average plus the red average, we'll end up with the gray average. So you can see the conservation of current there. Now, we haven't plugged in anything about the current in here. We just specified the correct voltages, and we end up with our electrons moving with the correct currents throughout this circuit. And so what you can do with this code, you can take any circuit that you receive as a problem using Kirchhoff's laws like we just used, and you can set up that circuit here in this code. I recommend starting with the one that we have here because you don't want to, create this geometry from scratch. You just want to make sure that your branches of your circuit always overlap, that you give them the appropriate resistance value based on their length and width and resistivity, and then you plug in the voltage and you can check to make sure that you got the current that you were looking for. So I'll let you give this a try with a problem at the end of the video. Thanks as always for watching. I will see you next time. Bye-bye.